All right. Thank you for having me. Good morning, everybody. Hopefully you're enjoying the session so far. I would like to say that I'm really excited and proud to be standing here because Nvidia has been using weights and biases tools for quite a while now, and it's really exciting to be up on stage here and to talk about that we both have two solutions that we're integrating together, so hopefully you'll be as excited as I am. Okay, so in 2022, I think we kind of all remember where we were. It's like that moment that hit when sort of not just the launch of a new technology exploded onto the landscape, but just that recognition of, wow, AI can work for me. And we all know what we're talking about. It was the launch of ChatGPT. And even though some of us in the field have been working on generative AI for quite a long time, it was the moment where businesses started to think about, wow, I can use this for my applications, and not AI isn't just images and video, but it's really about language understanding. So then what happened in 2023? Everyone started experimenting with generative AI, trying to figure it out. What use cases can I apply it to? Another thing happened was the launch of a lot of community models, so the ability to say, wow, maybe I can adapt this to my use case. And then in 2024, it's reaping the benefits of all of that experimentation and going into production. Now at Nvidia, we've been dealing with AI deployments and inference for a very long time. And so we work with hyperscalers who actually employ like hundreds of people who work on the optimization of AI models to put them out into inference for these latencies. But you know what? Enterprises don't have that time, and they don't have the resources to do that. And so I'm going to walk you through a little bit of a journey really quick about how we got to where we are and why we're building what we're building and announcing what we're announcing. Okay, so this is the most simple user workflow that you could possibly imagine that you started with in 2023. So it's really just the user, a prompt, an API to an LLM, and the answer. And everyone thought it was so amazing, and it was, until it wasn't. Because then you realize that, wow, this is hallucinating. It's just blurting out things that aren't factual. It's not talking about my data. It's not even talking in my brand voice. So maybe it's too verbose or it's too terse. And so in general, it just wasn't based in facts. And so then we added RAG. So you just talked about retrieval augmented generation to help with that factual data. So embedding your business data and putting it into a vector database and being able to retrieve it and cite it and then send that to the LLM to generate the answer. And honestly, I could stand up here all for an entire hour talking about embedding vector search acceleration and retrieval tactics like re-ranking, but I'm not going to, so you're welcome. But so you added that, and that was great, until it wasn't. Because then you started to think, wow, I'm sending all of this data and answers and prompts away to an API. And I did hear about this thing, all these community models that came out. And so with the launch of community models, it proliferated experimentation even further. And community models and these are just a few, right? We have a list of hundreds that we're working on. But community models were coming at first every month, and then it was like every week. And now I bet you're feeling it. Models are coming out like every day. And so how are you evaluating those models? How are you optimizing them? And how are you deploying them? And so the generative AI deployment options are seemingly endless. So what are the trade-offs that you're making for quantization, reduced precision, latency, compute footprint, just the total cost of ownership? Are you trying to deploy on a single GPU with a smaller model, but you're not getting the accuracy? Are you trying to do a multi-GPU deployment option? Or in some cases, and maybe you're not there yet, we have customers who are deploying multi-node. So that means 8 GPUs is in a node. And so like 16 GPUs at least to be able to serve these models. And so having to think about those trade-offs for total cost of optimization, total cost of ownership. And so then once you go to deploy, and you feel pretty good that you figured it all out, and then your IT and line of business is starting to asking you, is it secure? How do we get bugs fixed? What is this pile of code that you're handing me? Are there vulnerabilities in it? How do I deal with the next model? What is the API that you've developed and using? And so basically, you just start down this rat hole of everything that is not core to your business. Right? You are now spending all this time and maybe even building up a team that is not core to your business. And so it's enough to drive you crazy. And I think, look at this poor guy. He literally ripped his hair out. Trust me, I think my hair's been falling out over the last few years, too. So the Nvidia Nim, we call it NIMMs. Has anyone here heard of a NIM before? No? No? OK. So it originally we thought of it as an Nvidia inference microservice, but it's just NIM for short, and now NIM is just NIM. So it's not redundant, it's not Nvidia Nim, it's just, they're NIMs. And you're going to get used to it. Everyone's going to start talking about NIMs at this conference, I can feel it. And anyway, so we developed this NIM platform to have the flexibility to deploy your applications anywhere while maintaining control of your generative AI applications and keeping it close to your data. And so we basically simplified that deployment process for you for smooth operation for enterprise environments. So that means quicker integration and deployment for your teams. So let's take a look inside a NIM. And before I do, you probably noticed that all those little retrieval icons turn green as well for NIMs. And I can't stress enough that this is the most simple diagram of a RAG that you can see, because honestly, I didn't add guardrails, I didn't add prompt rewriting, query competition, query routing. There's many, many LLMs that are running for every single query, which is why you need to have the latency for every single LLM model that you have out there. OK, so let's look inside a NIM. So it all starts with the model at the heart. And we are proud to say that we work with what we call day zero LLM support, not just for community models. We go and curate the most important community models that we think for enterprise generative AI applications. But we also work with the world's most important model builders, so the people who are putting out new models seemingly daily. So the AI21s of the world, the Coheres, Google, Meta. So we're working with them before they even launch a model to make sure that the day that they launch that model that we have support in a NIM. And so now if I go down to the bottom, inference engines. So each model has a different optimization for every SKU, what we call a SKU, or a different set of hardware. So different hardware have different requirements or different features that you can exploit, the features and functionality. So an example would be floating point 8 in our Hopper generation of our GPUs, which wasn't available in our Ampere generation. So being able to understand which hardware you're running on to be able to exploit those features and functionalities. We also offer domain-specific code. So every model has a pre- and post-processing that happens for that domain. And it's kind of like Amdahl's law. So if you optimize the model, the LLM itself, you might be stuck in the bottleneck of the processing, the pre- and post-processing. And so for things like a generative ASR or an ASR model, you might have beam search decoding that you have to be able to accelerate, or different tokenizers for LLM. So all these domain-specific code get wrapped into the NIM as well. And also sometimes these are models themselves and they need to be co-located with the compute hardware so that can add latency. Again, you don't have to worry about that. We handle that inside the NIM. We also recognize the importance of customization, which we'll talk about in a little bit. So we offer the support of LoRa adapters within NIM to be able to serve multiple use cases per base model. We also offer industry-standard APIs. So if you saw that journey at the beginning with that red API that you started with, you don't want to have to rewrite your code or refactor your code. You want to be able to use the same API. And honestly, in some use cases, there are no industry-standard APIs. An example would be our generative model where we have what we call it audio to face, which is basically taking ASR and animating a digital avatar face. So there's no industry standard for that one, but we're working in the open to make sure that we're getting feedback on those APIs. And again, these are all built on our NV AI Enterprise blessed containers. So they're robust, they're tested, they're validated. We test them across various environments, including, again, we're hybrid cloud, so Azure, AWS, Google Cloud. You can make sure that they work across all these different environments. And then, and so basically, this is a NIM in a nutshell. And so let me talk a little bit about some of the core components that I get a lot of questions about, frequently asked questions. So LoRa adapters. So today's organizations have multiple use cases that they need to serve or customize for, but deploy on a limited pool of hardware. And so you can, as you start to think about customization use cases, it can quickly explode into, I need dozens or hundreds of models. But so instead of optimizing all of the weights, the full weights, what we call full fine-tuning of a model, LoRa optimizes a smaller subset of additional parameters that kind of represent the low-rank decomposition of the changes in the dense layers of the network, aka called LoRa adapter. It's so much easier to say LoRa adapter, just go with it. And so what does that mean for inference? That means you have a singular base model, and you're able to switch the adapter, and therefore the model's use case on the fly. And so you can have a smaller deployment, but be able to deploy many use cases of tens, hundreds, thousands, and it offers no impact to the latency of the model at all. So we do have customers right now with hundreds of LoRa adapters in production, and they're eagerly thinking about thousands. Okay, parallel strategies. I know you think about this every day. You probably wake up and think about parallel strategies. But so this can become tricky for larger models. Again, I'm just showing you the technology inside. You don't have to worry about it. NIM handles it for you. So things like we have what we call TensorRT inside the container. This is something that we've been building since 2016. 2015 was our TensorRT version 1. It's been around for a while. But so things like pipeline parallelism. And so what that means is it's interlayer. So you split the contiguous layers, sets of layers across multiple GPUs. Or tensor parallelism, which is intra-layer for the model. So you're splitting the individual layers across multiple GPUs. And then what we call expert parallelism. So if anyone here has heard about MOE models, a mixture of experts, being able to split the individual experts that are stored on different GPUs depending on the size of the expert, and being able to copy that the router to each GPU. And so all of that technology is handled under the covers for you. So things that we also think about is we're always thinking about performance. So things like custom multi-head attention, in-flight batching, quantized KV cache. So anything that drives performance, it actually drives a total reduction in total cost of ownership. Again, all of this is being handled for you, and I talked a little bit about per GPU SKU and the performance that you can get out of it by applying each little different performance to that, performance optimization to that. Now, these are just an example. This is not what it is. I'm just giving you an example of the things that you might think about. So if you have a Gemma 7B, and again, you want the latency, and maybe you go down to a floating point 8, well, you know what NIM does for you? We validate the accuracy. Because if anyone here has dealt with being able to do post-training quantization, you can find that if you go from floating point 16 to quantize int 8 or FP8, you might have some changes in accuracy. So we validate all these community models that there is no change in accuracy. We have, I think, the Mixtral, what do I have here? The 8x22B here is served on multi-GPU. But I'll give an example of one that's not here. So Llama 70B. You can serve that on 2 GPUs. But what we do is we actually quantize it to FP8, and we actually serve it on 8 GPUs, because that adds to the resiliency and the latency of the model and the serving that meet the latency requirements. And so these are the types of trade-offs that you have to have when people are thinking about, I want a more accurate model, but I want the latency to go down. And so we have customers who really said they wanted to deploy on a single GPU, but the larger model with higher accuracy was worth it in the end, because you want that delightful experience, and it's got to be accurate. And so they moved to the larger GPU footprint. But again, if you make that decision, the NIM's going to be able to handle that for you. OK, so I know you all were told a URL that you have to remember. I'm going to give you another one. It's build.nvidia.com. And so you can go out and experience all these community models that we put out there. We have Model Mondays, so we are releasing new models every single Monday. And sometimes, in some cases, during the week when that aligns with the model builder's launch day. And so you can go experience these models. We have APIs to play with, but then you can build, deploy, and manage with weights and biases, which we'll see in a second. And then you can deploy anywhere. Since we're going to talk about customization, I'm going to talk a little bit about what we call the Nemo framework. Nemo has nothing to do with the cute little fish. It stands for Neural Modules. We built this framework in 2018. It is still all open source. And the Nemo team, Nemo platform, is used internally for our own supervised fine-tuning, reinforcement learning, and our model building. And we actually use weights and biases internally within the Nemo team, so to track experiments and to enable team collaboration. And so it doesn't matter where an experiment is being run, whether it's on our internal or a co-located cluster at a desktop or in the cloud, the same experiences for tracking experiments is seamless across the team. But the Nemo is a full end-to-end framework for data curation, customization, evaluation, and then deploying. So I'm just going to talk about 3 microservices really quickly. So Data Curator is a multi-stage curation of high-quality data sets for both pre-training and fine-tuning workflows. And so things like text reformatting, deduplication of data. We love to accelerate things, so everything that we do is accelerated. So being able to take that from CPUs of 40 hours on a CPU of cleaning data down to 3 hours on a GPU. We also do document filtering, classifier-based filtering, and multilingual heuristic-based filtering, lots of filtering, and multilingual downstream task decontamination. And so what you do is that you take all these and then you blend it together to come up with your special data set blend for the type of customization that you want to do. And then you send that off to the customizer. And so instead of talking about features and functionality of the customizer, I'm going to give you an example. So we have a model that we built called Chip Nemo. It's our electronic design automation tooling. We did domain adaptive pre-training and fine-tuning on that model. And so what we did was we took some community models and we asked it, can you find the partitions in a design, write some Vivid code. And Vivid is our own proprietary coding language. Now, I'm sure a lot of you have dealt with enterprises who have their own proprietary coding language or their own APIs, and it's just something that RAG can't handle yet. It's fine for documentation, but literally can't generate code. And so when you ask it to generate this code, Vivid's a very common term that's very specific to NVIDIA. And this is why the importance of customization. And so you can see here that a typical Llama model gives you a theoretical paragraph and steps that you can take, but it's just like blatantly wrong. And you're like, fine, there's code generation models out there. So we did put it into a code generative model, which is not here in this particular deck. But what we did is it generated like maybe 20 lines of code that seemed really convincing, but it was just wrong. And so the real line of code was just a single line of code. And so this is how you get the partitions in a design. And this is, again, a proprietary language. And the gold standard that you would normally judge an LLM against of the task is about right there at the level of right below 60%. And you can see that using a larger model with domain adaptation gave an accuracy much above the gold standard and even better than the smaller model. So larger models and domain adaptation are something that you will start thinking about in the future for sure. And lastly, evaluation. How well is my model doing? Enterprises today, as I showed, have this option of all these different LLMs. We just saw a demo about evaluation. And so it's this, the Nemo Evaluator is a one-stop shop for either academic benchmarking to make sure that you're not drifting from the base model's capabilities when you go and domain adapt it, to even being able to use LLM as a judge, which we saw, and so even a platform for human evaluation and scoring. And so when you put all these together, this, being able to use all these customization microservices and evaluation and create custom NIMMs. And so it seems like a lot, right? You're like, man, I just want to be able to be an enterprise developer and deploy my LLM and not have to do anything. Well, luckily, Weights and Biases did integrate that into a platform for you to be able to do custom NIMMs and be able to deploy them. So I am going to invite Chris up to the stage. You can call him CVP. As everyone sees him, just go, hi, CVP, and come on up here. How are you? So Chris put together this amazing demo, but before we get to the demo, with some of the pain points that I talked about here, did it resonate with you? Do you see your users running into the same types of problems? Like maybe what's your favorite problem?
Yeah, for sure. I've been deploying web services for like 20 years now. And when you think about like a LLM web service, at first it's like, okay, I'll find a GPU and run like a Python server somewhere that just like calls the model. But it gets like very much more complicated than that very quickly.
Very quickly.
If I want to scale up, I have to like batch up the requests. I can't just call the GPU once at a time. I need to queue them up in memory and send them off. And then when you get into the world of like multi-GPU or multi-node, there's distributed, it's very, very hard computer science problems. So I am incredibly grateful that Nvidia has kind of thought about those things and made it a lot simpler for your average engineer to just get a service deployed.
Before we roll this exciting demo, how many here have tried deploying their own large language models for their enterprise applications? Show of hands. Is any of this resonating with you? Any of the problems? All of it. I just heard that. All right. Chris, you have anything else you want to add?
No, I occasionally get to moonlight as a machine learning engineer, and recently took a problem that we have at Weights and Biases around our support requests and made a little demo. So I think we're going to go ahead and roll the demo. You can listen to me do an incredible voiceover, if I might say.
It's great. Thank you, everyone.
Thank you so much.
Hello, my name is Chris Van Pelt, and I love to fine-tune LLMs. I'm going to show you how we integrated weights and biases with Nvidia AI Enterprise to compile and evaluate a custom LLM for a use case that we've been working on here at W&B. We get a lot of support requests from our users. We need to quickly triage and prioritize them so the most urgent requests are getting addressed as soon as possible. We created a dataset of support requests and their associated tags, such as priority, whether it's a bug or a feature request, and what part of our application the request is actually relevant to. The first step in our journey is to fine-tune an existing language model for our specific task using this dataset. We chose the Llama 2 7B foundation model. This dashboard is showing some of the experiments that we ran. From here, we can quickly find the best performing model to advance to the next step. Because we've instrumented all of our code with W&B, we're able to see the full lineage of datasets and experiments used to produce our fine-tuned model. Once we've chosen a model to deploy, we can promote it to our model registry. I've created a registered model named Support Llama 2 7B for our use case. This is now our team's source of truth for all of the models that are showing the most promise. At this point, we might think the hard part is over. In reality, we've just gotten started. There are still so many unanswered questions. How do we make our model run fast? How can we be sure our service is using updated packages free from vulnerabilities? How do we rate limit and monitor service usage? That's where NIM comes in. We've integrated our model registry with Nvidia Nim. A NIM is a secure and highly optimized container for deployment. You can think of it almost like an operating system. A NIM can securely execute Gen AI apps that generate text, images, audio, or video. Custom NIM models must be compiled for the specific accelerator they're meant to run on. I've started a W&B launch agent on an A100 with 80 gigabytes of RAM, which will act as our compiler. A launch agent is the equivalent of a CI or CD runner. It's constantly phoning home, asking if there's work to be done, and then executes that work when it's asked to. We can manually trigger model compilation from the registry UI, or we can integrate with our existing CI or CD system to automatically run compilation when an alias has been added. We've configured our automation to perform the compilation when the NIM alias is added to a specific model version. I can add the alias via the UI or do the same programmatically. Once I do, the agent picks up the task and optimizes our model for the exact accelerator we want to deploy to. After the model has been converted, it's saved as an artifact in W&B as the final output of our pipeline. Now that we have a NIM-optimized model, it's important to validate performance before we ship it to users. Our launch agent automatically runs the NIM service, so we can test it. We've set up an evaluation that asserts both the accuracy and the latency metrics we care about for our specific use case. We can verify that our model's performance is in line with our expectations, and then share this newly created NIM artifact with the deployment team. All of these steps have been captured in a central system of record, and many of the steps have been completely automated. This gives teams peace of mind in the ability to audit, debug, and optimize every component of their LLM ops pipeline. Because the final asset is wrapped in a NIM container, we can rest assured it'll be vulnerability-free and performance-tuned for the exact accelerator we're deploying to. That's W&B and Nvidia AI Enterprise. If you're interested in joining the Early Access program, sign up at wnb.me/nim.